Section 3.2, page 2. So when it comes to logarithm, if you don't see a base written, it's assumed to be 10. So if you just saw log of x, it's identical to log base 10 of x. And in terms of an exponential function, if it's base e, we refer to its inverse as the natural log, where e is considered the natural number. When it comes to a natural log, instead of writing log base e, we just write ln. We use ln in place of that, which implies a log base e. So I want to talk about some properties of natural logs, which I realize I covered in reverse order. So I'm going to cover these in reverse order now. This is the order it should be solved in first. Turns out the natural log of e is always going to equal 1. So how do we know that? So imagine I have the natural log of e, and I don't know what it equals. So what I could do is think of ln as actually log base e, and I'm going to rewrite this where I have e to the unknown power equal to e. But the only way that I could have a value here and these both be equal is if that value is 1. So therefore, whenever you see the natural log of e, we need to really think of that as 1. The second problem to solve is, or log property to notice, is if you ever ask the natural log of 1, it's always going to be 0. So if I have the natural log of 1 and I didn't know that it equaled 0, I would think of ln as log base e of 1, and I would rewrite that base to some unknown exponent equal to 1. Well, the only power I can take anything to and get 1 out is 0. So not just the ln of 1 equals 0, but the log of any base equals 0. Third, let's look at e to the power of ln of x. It equals x. So in this case, I'm taking this exact question, but what if I didn't know it equaled x? So I've got a question mark. What I'm going to do is take the log of both. Take the log of both sides. I'm not saying this very well. I'm going to rewrite it as a log, right? So we have log base e of some unknown value, and it's equal to whatever the exponent was. So now that I have this equation, I know that the log base e could be written as ln period. So if I've got ln on both sides, then these equations are only equal if question mark equals x. So therefore, e to the power of ln of x equals x. And the fourth property to share with you is if you're ever taking the natural log of the e of x, it's going to equal x. Generally, when we do this, it won't just be x. Maybe it's something like 5x squared, and so it would simplify to 5x squared. So what happens is I can use a property of logs, which we haven't covered yet, that says I'm allowed to bring exponents in front of the log. And we just mentioned over here that if you ever have the ln of e, you can always simplify it to just be 1. Whoa, sorry about that. And anything times 1 is itself. So notice that if you just have an ln of e or an ln of 1, we're going to get a numeric value. But if you see ln with e of x, whether it's as a log or an exponent, we're always going to just get x. Now let's talk about solving for x. And there's really two ways to do this. If you're given the equation e to the 5 minus 3x equals 10, really, the only way we've discussed so far is to rewrite this using the definition of logs. This base e becomes the base of my log. This 5 minus 3x comes on the right side by itself. And this 10 is what I'm taking the log of. But we said log base e could really be written as ln. So I have ln of 10. And now I just need to solve for this x. I would subtract the 5 to the other side. I would divide by -3, and I've got this answer over here. Now, using some properties of logs that we'll discuss in a minute, but you may already know, what I'm allowed to do is if I have this original equation in black, which I leave over here in black, I can take the natural log of both sides. Now realize I chose the natural log versus log base 10, base 2, base 17 because of this e, because we have these special properties up top that if I ever see the ln of e, I can simplify that to 1. So now what I'm going to do is take the exponent and move it out front. And this leaves me with just the ln of e, which we said we can rewrite as 1. And 1 times a binomial is just that binomial. I have not touched the right side. But now, as I solve for x, I'm going to subtract the 5 to the other side. I'm going to divide by -3. And you'll notice I get the exact same answer. Similar thing happens to the problem on the right. I'm given an equation here instead of an exponential question. I'm given a log question. Well, in terms of logs, we know how to use the definition of log and rewrite it as an inverse. So I'm going to take ln and rewrite it as log base e of the binomial equals 5. My binomial equals 5. So I can now rewrite this in the exponential form of e to the 5 equals the binomial. And now I can solve for x by subtracting the 3 to the other side and dividing by the 2. Or using the properties down below, since I have ln in the question, I'm going to raise the question, it's all in black, I'm going to make it the exponent of e. So I've taken e to the left side and e to the right side. Over here we said if you ever have e to the ln of x, whatever the natural log of, that is what you can reduce this down to. So if it's the natural log of the binomial 2x plus 3, I can reduce the left side down to 2x plus 3, where I keep the right side the same. And now I solve for x by subtracting the 3 to the other side and dividing by the 2 to have the exact same answer. So now let's go ahead and talk about those properties of logs that I should have probably already covered. Don't forget, if you ever have the log of a product, you can then write it as 2 separate logs that are added together of the terms of the product. Or instead, if you have a single log of a quotient, you can write it as 2 separate logs that are subtracted of each term of the quotient, the numerator and the denominator. And lastly, if you ever have a log of a value that is to an exponent, you are allowed to pull that exponent out front and just leave it the log base a. And really you can use the product formula to help figure out how that exists. So now I'm specifically asked to use those laws to expand an expression. The reason we're going to want to do this is we're going to have to take derivatives of logs in a few minutes, and this is pretty messy. But if I were to expand this first, where I want to address the division, I'm not saying that well, so I'm looking at it as the log of the numerator minus the log of the denominator, I can continue to expand from here. A squared times b is a product. I cannot pull the 2 out yet. It would only be if the 2 was outside of the product. So I can break the product into 2 logs of each term of the product. And in the case of square root of c, I can rewrite that as an exponent and then pull that exponent out front. And lastly, I can go ahead and pull that 2 out front. Now, in other cases, you might be asked to take derivatives that are challenging, and you can actually simplify your problem by writing it as a single logarithm. Now, even though it may be tempting to see the plus and the 2 separate logs and want to make this the product of 3 times 7, I'm not allowed to do that because in front of the 3 is not the log of 3, it's 2 times the log of 3. So I actually need to pull that exponent up front first so that I really have 3 squared, which is 9. Now that I have just a natural log on the left and a natural log on the right of my plus sign, I can use the product rule backwards to say they were originally a product of 9 and 7 and get a final answer of natural log of 63.